Yeah, good morning, everybody, and welcome to Bioprocess Engineering. It's quite a while that we didn't see live, but welcome back again. Today we will talk about kinetics, but before talking about kinetics, we will have a look at the homework. One, I think, was very simple. It was just using the formula we have used in the lecture and doing the conversion for another uptake rate. And the second one was simply estimating the KLA using the simple dynamic method. All examples in this section are based on the Bioprocess Engineering Principles, second edition, Academic Press from Pauline Duran. The solution path is also depicted in this book, so please refer to this book for details, and it's again a warm recommendation to have a look in this book. And you see we have stirred a culture of these hematopoietic cells, and these were the results we have obtained, and the dissolved oxygen tension is 78%. Electron response did not vary. For the RPM, response time was 2.8 seconds. And measuring was repeated nitrogen sparging, so it was measured in culture and it was measured with nitrogen sparging, and the KLA was similar. So that's, by the way, that's important. You remember that the speed of the sensor must be high enough in order that we can assess the value appropriately. And second, we need to know whether there are dynamic effects in the bioreactor which break our results, and this is not the case. And then the next point is the stir, whether this is a problem, whether if it forms a film, and this is also not the case. So the calculation was very simple, so you had no questions, so therefore I will just briefly have a look on what was to be done. So this is then T, and this is, you remember, ln the saturation concentration of oxygen divided by the oxygen saturation minus the actual oxygen saturation. No, not in this case, not at the end. This is the actual one. And this is what you plot, and then you get this curve. And of course, you need to be here. And well, what you do is you take these two values, and this is what you measure. So what you do for your calculation, PO2 minus, so of course in the liquid phase, that's clear, minus the actual concentration, the saturation, sorry, I'm always telling concentration today, of course it's saturation in this case because it makes our life easier. One is equal to KLA T2 minus T1. That's just because of this equation. And then if you put that in one equation, then this is very simple. If you divide, then of course this kicks out, and then KLA is equal to, because the saturation concentration, sorry, is always the same. This I could put like this, and then I simply put now my saturations. I have where I just have to look it up. 78 at the end, and here at the 2 points is 50% and 66%. Okay, so it's the one is 78 minus 50 divided by 20 minus 5 seconds. So this is of course this value, this is this value, and this is then equal, if you put it into pocket calculator, 0.056 per second, and that's a fair value for the cultivation of animal cells, I think in this case, or hematopoietic cells, yeah. Okay, now next chapter we come to kinetics. So that was it about mass transfer. You have learned it's important mass transfer, and now we will have a look into kinetics. We talk about kinetics. We are at the kinetics part, and we will talk about basic reaction theory at the beginning, and we will talk then about yield and cell growth kinetics. Yeah, that's what you should know. And let's start now with the basic reaction theory. Again, what I tell you here with respect to kinetics and reaction theory should be the same as what you have heard in chemical reaction engineering and thermodynamics and so on. So of course it's not different. We are just here, let's say, looking especially in things where these biological parameters are relevant. So that's the difference. The basic theory, of course, has to be the same. It would be a problem if in bioprocess engineering we reinvent the world always. Yeah. So we have two parts in reaction theory, and this is, of course, something you know. We have the reaction thermodynamics. In other words, how far can the reaction proceed? And the reaction kinetics, that's simply the rate at which a reaction occurs. Now, the question you ask is what determines actually the extent to which reactions are converted to products. And there are two basic answers here. Of course, the thermodynamic equilibrium of the reaction. If it's a reversible reaction and you reach an equilibrium where, let's say, the conversion of substance A to B in the equilibrium, it's 50%, you cannot proceed further than this 50% in this condition. If you start with 100% A, you will end up at the end, if you run it long enough, with 50% A and B at the end. There is no way to go further. And also, of course, you might have alternative reaction paths and so on. And then this is, of course, also going down the extent of product, of your wanted product, which is being formed. And this is both considered in the so-called reaction yield. So both parameters go into this reaction yield. And you already have the feeling that for us, in biological systems, you will always have an alternative reaction path in cells, and you don't know exactly the path. So therefore, in contrast to chemistry, where you can calculate then a reversible reaction, you can set up the equation for a reversible reaction, and this is what you have done in chemistry, and then you can set up an equilibrium content using this equation, and you have a temperature dependency. So you could, of course, say what happens if I move the temperature. Then you see that you have a change in the standard free energy. This is interesting. If you think of this methane pyrolysis, then you can shift to another direction, even if the specific heat is less affected by temperature change. The delta G, of course, is the Gibbs energy. So this is what you have learned in chemistry. However, setting up such an equation in general in biological systems is more difficult. Now, the reaction yield corresponds to the extent to which reactions are converted to products. That's logical. Yeah? So there is a general definition, and we will talk about yield coefficients more precisely later. But the general definition is the yield is the amount of product formed or accumulated per amount of reactant provided or consumed. However, there is no real strict definition, so the actual yields might differ from book to book and place to place. So always check what does this yield they are talking about actually mean. Therefore, what we want to learn here is first of all the concepts of yield. So these are some yield definitions. You might hear other names for that, but just what it means. We have the true stoichiometric or theoretical yield. This is the mass or moles of the product formed divided by the mass or moles of the reactant used to form that particular product. So that's already here, you see always mass or moles. A yield could be a mass yield, or yield could be a molar yield. And of course, that makes a difference. It is if you have 1 grams per gram, this is not exactly the same as 1 mole per mole. It depends on the molar masses of your of the reactions involved. The observed or apparent yield is mass or moles of product present and mass or mole of reactant consumed. So the difference here is this is the reactant you know which is going in this reaction, and the other one is the mass or mole of reactant consumed, which just has disappeared. For reversible reactions, we also talk about the gross yield. So this is the mass or moles of product present divided by a mass or moles of reactant provided to the reaction. In a biological system where you have a fermentation reaction or something like this, the overall reaction is irreversible. So the reversibility is for our systems is if you look at in enzymatic reactors also. So for technical enzymes this is relevant, but if we do fermentations, you won't see an overall reversible reaction. Remember, if we produce glucose, if we use glucose to produce ethanol, there are tons of reaction in between. We don't care if we do the calculation. Of course, we were excited to look at how glycolysis works and how then ethanol is formed. But if you just look at yields and so on, you're not so interested in the metabolism in between. You want to optimize what's getting out, and then of course the overall reaction is irreversible. Going back to our example. Our example was that the glucose isomerase is used for the industrial production of a high fructose corn syrup, catalyzing the following reaction. Glucose goes to fructose, it's an isomerization. In parallel, you enable the spontaneous isomerization of glucose to mannose for whatever reason. This doesn't make necessarily sense, but this is just to show you how this works. Now, in a continuous industrial process, the reactor is fed with glucose and converted at 60 degrees to fructose using glucose isomerase. 40% gross yield. That is the first value we have. 40% gross yield is correct, or 40 grams per gram. So in this case, I would always give yields not as percentages, give them as gram per gram, but it's correct, 0.4 gram per gram. Now let's see how this works. Also for yields, you will need to do mass balances in this case in such a system to know what is happening there. So it's a reactor, feed stream, and the product. And in the feed you have just glucose, and you have 10 grams glucose. In the product stream you have 4 grams fructose, and I have 0.5 grams mannose. And you already see by eye that you also need to have glucose. So you have also glucose. So you see that you first have to finish the mass balance before you can start doing the calculations. The mass balance total is M in and is equal to M out. Total is M in is equal to M out. So M out therefore is equal to M in is equal to 10 grams. It's per hour maybe, but we don't care. And this is of course this equal to M glucose out plus M fructose out plus M mannose out. So this is, many already forget that. This is very simple, of course. You see it by eye, but it's very easy to forget that. So the M glucose out is equal to 10 grams minus 4 grams minus 0.5 grams, and this is equal to 5.5 grams. For the observed or apparent yield, we have the reactant consumed. Yeah. So for the reactant consumed, we need to know how much glucose is being consumed. So we need to do a glucose balance. So there, it's of course m glucose in plus m glucose generated here at steady state is equal to m glucose out plus m glucose consumed. M glucose generated is of course 0, so therefore we have m glucose consumed is equal to m glucose in is 10 grams minus plus m glucose generated is 0 plus 0 minus m glucose out, which of course just goes at the minus over there. It's 5.5 grams. So we're at 4.5 grams. So now we have all the values. What we do now is simply we look at the yield coefficients. Yeah. So now we have our stoichiometric yield. Remember, it's the mass product formed divided by mass used for the reaction. And now we have done tons of calculations, but we know that we have 4 grams of fructose. That's our product. And by stoichiometry, we know that it's an isomerization. So that's what we take from the stoichiometry. So the fructose generated is the same as the fructose out. That's clear. That comes from the mass balance. And glucose consumed based on stoichiometry must be the same. So it's also 4 grams. So it's 1 grams per gram, the stoichiometric yield. So now we come to the observed or apparent yield. Consumed in this case. So we have again our 4 grams. And now we look at our glucose consumed, and that's 4.5 grams. And therefore we end up, we put that in our calculator, 0.9 grams per grams. And by the way, of course, this is the same as 0.89 mole per mole, as it's an isomerization again. And the molar masses are the same. Okay, now we come to our gross rate, and this value we have already heard should be 0.4, and now let's see whether that's correct. And therefore it's 4 grams divided by 10 grams, because glucose in was 10 grams. 0.4 grams per gram, and of course that's the same as mole. You see, that's very simple. But also here, as you have seen, is I have set up a mass balance. This makes sense because then I am sure that I did not forget something. Now let's see whether there are remaining questions. Why would glucose be on the product feed? Don't we assume complete conversion? Even if we would assume complete conversion, it's an reversible reaction. You would always assume that only parts of the glucose are isomerized because it's reversible. And we didn't put here what is the equilibrium, but if it's 50%, we are already happy here. So if the reaction takes not long enough, because you have a plug flow reactor, for example, you also might just achieve 30%. So this is a real world example how this could look like. Yeah, you have your enzyme immobilized, for example, in your reactor, which can do this isomerization. The thermodynamic maximum possible yield might be 50%. By the way, I don't know what the where the equilibrium is, and of course it also depends on the condition. I especially don't know by heart where it is at 60 degrees. Let's just assume it's at 50%. But if you go quickly through this reactor with your 10 grams glucose, and the reaction has no time to reach the equilibrium, you might end up with just 1 gram glucose at the end. So just parts of it is converted. That's one problem here. Parts of it are just converted. And the second problem is that we had the side reaction. Whether it's wise to run a reactor like this that only 45% of the glucose which go in this reactor then can be converted. This is a matter of debate, but you are close to this 50%, and you expect, if it would be 50%, to have 5 grams glucose left. You have 5.5 grams glucose left, so it depends on the equilibrium. Honestly, I don't know it. So this could be perfect, or this could be further optimized. How does the stoichiometric equation make sense? Aren't we converting 4.5 grams glucose to 4 grams fructose plus 0.5 grams mannose? Yes, but what we calculate is the true stoichiometric yields. So we always are interested in glucose. This is our product. So in reality, you wouldn't even know that you generate mannose. This might be a whatever side reaction. You want to see the yield of your fructose being produced. You don't want to calculate yields for all products being produced, but just for fructose. And the true yield, of course, you just have your fructose is always your 4 grams, but to use that product based on your stoichiometric, your chemical equation, your isomerization, you produce 1 gram fructose from 1 gram glucose, full stop. Yeah, so that's straightforward. So the observed yield is the real yield what we get out in theory. Remember, in this case, it was given that mannose is being produced. It could be that you don't know what is being produced, or in general, you might have biomass growth. It's respirated into carbon dioxide or whatsoever. So for that reason, the observed yield is always smaller than the true yield. Okay. We have talked about yields, and the next general thing are rates. So we have set, this was at the board, we take a general irreversible reaction in this case. So we have A plus BB. The reactants give the following products with stoichiometric coefficients. If we set up an unsteady state mass balance for this system, we have the change of the mass versus time is the mass which goes in minus the mass which goes out plus the mass which is being generated minus the mass which is being consumed. So this is our general mass balance. And if we say Ra is the rate of reaction with respect to A, we then can write dMA over time is MA in minus MA out plus minus, sorry, for MA. MA is just being consumed. So RA consumed is RA. R generated is 0. Of course, that's not true for Y and Z. There is the other way around. So we have then just based on this mass balance minus Ra. It's just consumed. So this term and not this term. Yeah. Okay. And now, if we say a closed system, then of course MA in is MA out is 0. This is of course a specialization. We simply kick out these two, and we have our RA is minus dMA dt. And accordingly, you can do the same for RB and for RY and RZ, and you will see as RY and RZ, we don't have this, we have not the consumption, but we have the generation. Therefore, RZ, for example, will look like this. RZ is dm z dt, positive sign. I just have showed you in this long presentation that you believe me that the signs are different. This comes from this unsteady state mass balance. Yeah, so Ra is minus dMA dt. Rb, of course, is also minus dMB dt because it's also consumed. And Ry, Rz is a positive sign, dmy dt or dmz dt. So these are the rates corresponding to the masses. And if you look for reaction rates for the reactants, this is also set a consumption rate because they're consumed. And for the products, remember it's an irreversible reaction. These are called production rates. Now, the total rate is the rate for the complete system. That's what we have looked at, the complete masses. But of course, usually you're more interested in the volumetric rate. This is the reaction rate per volume, and you could also, and then of course you just divide that by the volume. If we are in a closed system where we don't put something in or out, then the volume is constant. We can take it out, and then is of course the concentration divided by dt, dCA dt, but this only works if the volume is constant. The specific rate is the reaction rate per quantity of enzyme or cells, and this is how I can define that then based on that, either based on the masses or the concentration. Usually, of course, I use this equation where I have the volumetric rate divided by the concentration of the enzyme, because then, of course, it's normalized. And now you just see my head here. Oops, no, I see too much head. Now it's enough head, but not on the rate. So we have here the rate, and this is concentration divided by the enzyme units, for example, or the cell concentration. So that's usually the rate you work with. Okay, now that's about the reaction rate. And of course, now we click through because this is what you already know from thermodynamics. Of course, you have a temperature dependency of the reaction rate, and you have a dependency on the concentration, and you can express that using the following equations. And of course, then you can measure this rate constant as a function of the temperature. If you plot then log transformed it, then you normalize that and you have linearized that. And if you plot then 1 divided by t, you can measure ln k. So this is normalization, but this is of course something you will certainly not find in the exam. However, you will do an example where you need this equation, and you have of course this equation also in your formulary. Now we have talked about basic reaction theory, and now we will have a look at yield coefficients. So yields in cell culture. So again, we were now at very, let's say, theoretical background reaction theory. That's what you have already learned. That's just repeating what you know. And now let's go to the real world. We're in cell cultures. Usually we have cells around. And what is the special feature there? In cell cultures, we don't have that, what we have seen in the example before, that we can say we have our fructose, our glucose, which is isomerized to fructose, and then we have analyzed and we have seen that the single reaction we can define, we go to mannose. So we have in a cell culture or a cellular system, we have many reactions which are overlaying. So we usually have no idea what is happening. Of course, in systems biology, you approach that, but in most cases where I wanna just produce product X, we will not go into analyzing the complete metabolome and the complete space of reactions and so on. And nevertheless, for yields, it doesn't really matter if we know everything or not, because we can of course measure under certain conditions. If we put 10 grams of glucose in, how much fructose is coming out, this we can measure. So no, the advantage is we don't need to know what is in between. So also here, of course, the yields are expressed as yield coefficients or yield factors. And the general definition of a yield coefficient is simply the yield factor, where you put this J in subscript, then what you look at is then the mass or moles of J produced divided by mass or mole of K consumed. And also here, of course, you have a minus, because if you calculate here the deltas, you will get a negative, overall negative value without this minus, and you want to have a positive yield coefficient at the end. So therefore, this minus is here. Okay, and you just as a list of yield coefficients which are routinely used. So you see, one is the mass or moles of biomass produced per unit mass or mole of substrate consumed. In general, these are mass yields what you're interested in, because mole biomass don't make really sense at the end. You don't really can hand that. So this is the biomass yield, and this is certainly one of the most important yields, or the same is true for the product yield, because this is usually what you want to do in your bioreactor. You want to produce biomass, or you want to produce your product, and you might want to produce as a low amount as possible of biomass. You want to optimize then these parameters. At the end, you want to produce as much product as possible from your substrate. If you go for ethanol production, if you want to produce bioethanol, you want to put as much as possible of your substrate in your ethanol and nothing else. You don't want to produce much biomass in this case. So you will optimize this yield coefficient. Of course, you can also look then, you can vary that. You can also look at mass or moles product formed per unit mass or mole biomass formed. And what's often also used is mass biomass formed per mole oxygen consumed. This can also you have directly in your reaction equation. Now, the respiratory quotient we have already talked about. This is simply the carbon dioxide formed per mole of oxygen consumed. And you remember, this is a parameter we like very much, because we can use that for our stoichiometric balancings in order that we can do that. We can also then look at parameters which are inside, for example, the mass or mole biomass formed per mole of ATP formed, and so on. So you see, you can define an endless number of yield coefficients, and the most important ones are, of course, these ones. This one is also something which you will see from time to time, and also this one. But you can define at the end your the yield coefficient you want, depending on what you need to do. Okay, so now let's come to an overall and instantaneous yield. I prefer seeing me down there. I don't know what's by the way, I don't know what is the best way, being on the top or being down there, but I'm just preferring to be here in my little edge. I'm more happy, so therefore I always, if possible, go back there. In batch culture, the overall yield represents the difference of J and K between final and initial states. However, so if I'm in my culture, this might vary. So yield coefficients are not necessarily constant. So if I have a variation, I need to print the instantaneous yield if I'm interested in the yield as a certain time point. And this could be different to the overall yield, of course. Yeah. In a closed constant volume reactors, you can calculate the instantaneous yield. You remember our yields, Jk, was this minus delta J divided by delta K. So this was true, this delta, if we have at J at the end and at the beginning, the same K at the end and at the beginning. Now we talk about instantaneous yields. So now we want to have a value where delta K goes to 0. So this is at a certain time point. And then the minus delta J instantaneous Yjk is equal to delta J delta K. And this is then, of course, minus dj dk. And I can now also write that as minus the change of the reactant J over time divided by dk dt. no, not minus, sorry. Here, of course, no minus. Sorry for that. So minus dj dt divided by dk dt. And this is nothing else than minus dj dt is my rate Rj. Rj, remember, we have talked about this volumetric rate. Rj is minus dj dt. That's what we have deduced before, divided by, and everybody should be able to read that, Rk. Just if I know my rates Rj and Rk, at a certain time point, I can directly calculate the corresponding yields. So let's see whether this is also on our slides. And it is, and that's good. Okay, so this is then the instantaneous biomass yield is the specific growth rate divided by the specific substrate concentration rate. So as this, I can calculate yield coefficients. And if you see that, you can then also use this to convert yield coefficients. So if you want to go from yxs to y OS, for example, and so on, then you can use this via the rates to directly convert that. Observed yields in cell culture. So the theoretical biomass yield corresponds to the yield which would be achieved if we channel everything into cell growth. This is the maximal thermodynamically possible yield. You remember we have done calculations in our mass balance section using electron balances where we calculated the theoretical yield. However, you will always see that some substrates will go for non-growth activities, other products or whatsoever. So this yield which could be achieved is reduced. And the observed yield is therefore taking account everything, whether it's going to biomass growth or something else. So this is, of course, the value you see. And the observed biomass yield, just by definition, is then the difference of the biomasses divided by the substrate consumed. And the substrate consumed, you can then put together, this is the substrate which goes to the growth, plus the substrate which is not used for growth. In general, you don't know, you can measure these parameters, so you can just deduce from thermodynamics, stoichiometric conditions this, and then you see what it's going to the other parameter. Of course, what you want to get at the end is you want to get this observed yield as close to the theoretical yield as possible, if growth is the intention, what you want to do. And this is just some observed biomass yields for microorganisms and substrates, and you see that we are around about at 0.5 grams. But of course, this equation here reflects what we have seen in our electron balance sections. So if you grow on methane, your observed yield is higher because the energy content, because the degree of reduction of methane is way higher than the degree of reduction of glucose. You can produce more biomass, and we have calculated the maximal theoretical yield, thermodynamically possible yield, using electron balances. You remember. But you see, of course, in reality, if you remember what we have done there, you remember that the maximum theoretical yield for ethanol was round about double as high as the amount of the yield for glucose. But in reality, it is lower because it's more difficult to metabolize ethanol. That's the good news. So you don't just gain double of the weight if you grow on ethanol. So these are the observed yields. And now coming to an example, we have Acetobacter acetibacteria, which are in a aerated medium containing 10 grams per liter ethanol. After some time, we have 2 grams per liter ethanol, and the acetic acid which is being produced is 7.5 grams per liter. So we don't produce biomass here. So how does the observed yield of acetic acid from ethanol compare with the theoretical yield? We have Acetobacter acetii in our medium containing 10 grams per liter ethanol. and after some time ethanol is 2 grams per liter and 70.5 grams per liter acetic acids are being produced, and our reaction is, and this is already balanced. Make sure to check it if you're not sure. And now we go for the observed yield, and so it's the Y. We are always looking at the product per substrate, so it's minus delta P divided by delta S, and we had, based on the exercise, 7.5 grams are in the off stream, so it's minus 7.5 minus 0. Nothing is getting in. Just put the grams also. 7.5 grams minus 0 grams divided by, out it's 2 grams minus 10 grams, and this is then 0.94 grams per gram. I think in this example they have in the Duran they put it the other way around, so that's not nice. This is the correct way. So this is the observed yield, and now we have theoretical yields. This we take from the stoichiometric equation. Now let's come to the yield. So it's YPS, and we see based on this equation, of course, 1 mole of ethanol is used to produce 1 mole of acetic acid. We like these equations where we have mole to mole, so is 1 mole acetic acid is our product divided by 1 mole ethanol, and we just put the masses. So of course 1 mole acetic acid, and if you calculate that, we have 60 grams per mole, and the ethanol we have 46 grams per mole. So our mass yield is 1.3 grams per grams, and our molar yield, if we would write that simply other way here, is 1 mole per mole. If you then just compare that and calculate in relation to the observed yield, we are at 72% of the theoretical yield. We will also produce biomass and so on. We will aspire, and so therefore it might be that this is okay. Of course, you want to optimize that. In order to be sure that you're okay, you would need to look up literature values, but often these values are hard to get, so therefore you need to fiddle around with the conditions. Sometimes it's for your special reaction, it's difficult to get then hands on real literature values. Okay, so we are at the end. Let's see whether there are still for calculating observed yields, did you use equation 21? Yeah, it's observed. Yeah, 21 is observed biomass yield is the change in the biomass. It's in this case not the biomass, it's the product, but it doesn't matter, divided by the total mass of substrate consumed. Yes, so it's simply here, of course, I'm talking about here I'm talking about product, but of course the yield observed and theoretical, the equation looks the same if I look the product yield or if I look the biomass yield. And of course it's the substrate which is being consumed. I don't see in this reaction here what part of the substrate goes into the product and what part of the substrate goes in other directions. So this is therefore the substrate here consists of the substrate which goes into the product plus the substrate which goes into something else, which is the observed yield. And this is exactly what is written in equation 21 for the biomass. Then that's it for today. Thank you very much for your attention. Have a nice weekend. Looking forward to seeing you next week. No homework today. I'm so sorry. But I hope that next week this will be better. So then enjoy the time without homeworks. And I talk to you. You might have a look in glycolysis and so on if you feel, ooh, it's good that the professor didn't see me. So goodbye and looking forward to seeing you again next week.